This is basically is a high-level summary of CCUS and SynBio research conducted by my team. Yeah. So everyone remembers, I just said the total CO2 emission every year is about 37 billion tons. And how much we need to remove by 2050 is about 10 billion tons annually. So anyone wants to guess how much CO2 are we using now every year? Who wants to guess? Question, you know everything. So what's your guess of how much CO2 is utilized every year now? Roughly. It's a good answer. Yeah. So the CO2 use is actually currently less than 500 million tons. It's a huge difference. Million, not billion, okay? We're emitting 37 billion tons a year, and we're only using 270 million tons a year. And how do we use it? Majority goes to make fertilizer. And then there's some use in the material, so like food, fabrication of metal, and so on. But the key message here is in totality, we are using less than 500 million tons, while we are emitting 37 billion tons. So why is that? So let's look at the CO2 source and the concentration and the capture cost. So it's easiest to capture CO2 in natural gas processing because it's very highly concentrated CO2. Our venture partner Jean-Claude Pierre is going to look at cement CO2 capture, but actually it's very difficult because it's very costly. Because the CO2 from cement manufacturing is actually low concentration, so it's only 30%. But if you look at the number, it's like $15 to $100 per ton of CO2, which doesn't sound so bad. But anyone wants to guess how many plants in the North America that is doing carbon capture and storage? Who wants to guess? Stefan, what's your guess? Three. Stefan says 3. Question, what's your guess? Less? 2? Okay, I want to say there is literally only 1. So one new plant right now in Canada is doing this carbon capture and storage. And one before in the US was doing it, but shut down last year because it's so expensive to run. So why is that? So Patrick digged up that number. Basically, to capture carbon and store it, each project costs around $1 billion right now. Because to capture is one thing, and then you have to store it, you have to store it underground, and the construction cost and the capital cost is just tremendous. So why aren't we using it then? And why don't we just capture it and use it? So we always look at it from first principle, right? CO2 is a very, very inert molecule. So it's actually very, very difficult to break CO2. So we sort of divide, my team made a huge table, but in my mind, roughly speaking, we are looking at basically 2 parts. One is CO2 direct incorporation. You will hear later afternoon about CO2 going into cement. You will hear from Econic CO2 to a polymer or polyol. Those are relatively easier to do because you are taking the whole CO2 molecule and put it into something. so into gasification or into polyol, polyurethane. So that's why I believe today the only VC-backed startups that kind of generating some commercial revenue is in the CO2 to cement or CO2 to poly or CO2 to material space. And then there are many startups working on the right-hand side, which is CO2 splitting, which requires you to take CO2 molecule becoming CO, which you have to either do it by electrochemical method or you do a thermochemical method and so on. So that's very energy intensive. You need a catalyst, you need energy and so on. So it's quite expensive. And a reason why it's not widely commercial yet. There are many startups working in it. So that's the reason why we are not utilizing CO2. Fundamentally, because CO2 is a very difficult molecule to utilize. So this is a chart from another research report about how close the technology is to commercialization in terms of CO2 utilization. So you can see from the top, which is commercial now, to very far away, which is more than 20 years away, but we will probably need it to utilize the CO2 the scale that we need. So I'm not going to go through the details, but roughly speaking, it's like as I said, what's commercial today is if you don't have to split the CO2, you just take the whole CO2 molecule and put it somewhere into cement or into polymer or anything else. It takes time to reduce cost. That's the basic of it. So I said the commercial one is the CO2 Carbon Mineralisation, which is the CO2 to cement into cement kind of application, where you basically react with the carbon, the other called gasification, you calcium oxide, and then you become calcium carbonate. That is the basic principle. And many startups, many are well known in the field, working on CO2 incorporated into cement. And I want to say we have looked at everything. Every single company owns this slide. We literally, and I think our LP Petronas invested in Solidia, right? Yeah. It does work in the US or European market. It just doesn't work very well for China because Chinese cement or the concrete already has a lot of fly ash and mineralization and so on. So to add a little bit more CO2 into the Chinese concrete doesn't make economic sense. But in the US, where there is more pure, the concrete, to add some CO2, it does make some sense, but still, it's only like a few percent of CO2 into the cement. So Carbon Cure, Solidia, those are all leading companies in the US and very well VC-backed. The next is CO2 to Polio. We will hear a ton from our portfolio's Keith is here from Econic. That's what they do, CO2 to polio. And basically, yeah, here, so the play field is relatively few. We have two larger companies like Aramco and Covestra, and those are large multinational companies. And then we have Econic, the CM portfolio company based in UK, and Puli, based in Zhejiang in China. So we highlighted the difference here for Econic with the other players. Basically, with the invention of a new catalyst, Econic is able to reduce the pressure that is needed in this reaction, which makes it hugely more feasible. So I'm not going to steal the thunder of Keith. You will hear from him how Econic does it and why it's different than all other players using DMC catalyst. Then the next one is electrochemical splitting of CO2, where you apply you add water, you add renewable energy, and you produce, you split the CO2, you produce chemical. Yeah. And there are many startups also in this in the field. And I'm not going to go into each detail, but I want to say, as you can see here, the conversion efficiency is in general below 50%. There's only 50% conversion efficiency. And in addition, because most of these processes use water, so it's very easy to split water into hydrogen instead of splitting the CO2. So you have competition between splitting the water and splitting the CO2, and then you end up with a very difficult separation process. So that's also the challenge of this type of reaction. And then we have this beautiful, very complex chart that Mason did for algae carbon capture and utilization. Basically, you are using microorganisms to take CO2 and convert into different material. And there's loads of companies in this field. So BASF invested in LanzaTech, which is a very good IPO, did a good IPO, and then we have many startups that we can't fit on this chart. I think Yuanyu Shengwu is here at the conference. They are trying to take the algae and convert CO2 to useful material. So right here is it's a good pathway to biomanufacturing, this next topic, because we are talking about algae. So US came out with bold goals for US biotech and biomanufacturing only in March 2023, which I read and I was a little bit shocked because of the high number here. If you look, there's in 20 years, the goal is to convert bio-based feedstock into polymer that will replace today's 90% of the plastic and other commercial polymer. I don't know how company like SABIC and so on think about that goal, but 90% of the plastic goal is to be replaced by bio-manufacturing. And then 30% of the chemical demand will be done by bio-manufacturing. That's the US goal also in 20 years. It's in 20 years, it's not tomorrow, but it's a very ambitious goal. And then in 5 years to sequence 1 million microbial species and to get 80%, more than 80% of them function and understood. So biomanufacturing is really coming. That is a very big shift in terms of how we produce chemicals and polymers. I have 1 minute, I see. So I'm going to skip this slide. So basically, a lot of VCs are investing in it. And the reason that it's becoming popular today is really because of the advancement in IT. So you can have bioinformatics and computer science to do this cycle, which is design, build, test, and learn. You need a lot of these cycles and computational power to understand the relation between the genome and how you microbe and how you engineer it and so on. And SynBio has many startups in the West. I actually looked at embryos like 2006 and 15 years later, it's still not profitable. It's a platform company. I really can't finish in half a minute, but let me borrow for a few more minutes. Basically, there's a traditional fermentation process, which is a traditional synbio. You ferment, you engineer the microbe, and then you do fermentation, and you produce chemical, and you do this cycle. The next frontier that we actually believe is cell-free, because when you ferment, basically there are a couple of issues. A, you would have limits in how much microbe you can put in the reactor, right? Because too much, the microbes die. And therefore it has a limitation on how much chemical concentration you can produce in fermentation. And then after you ferment, you have to break the bacteria cell, and then you have to purify it, and so on and so forth. So the cost is very high. If you can do it cell-free, which basically means outside of a microbial environment, and do it with the bio process, then you will be a lot quicker and cheaper. So, but you still go through the same process, the design, the learning, the testing, and then you test again, and you measure. So we looked at Chinese companies. We literally looked at more than 50 startups now. We put them into basically two charts. One is a platform versus product. One is more than 5 years. The other is less than 5 years. And basically, in short, in China, there's no one doing pure platform. Everybody is doing platform plus product, because otherwise you can't survive. And secondly, we do believe you need more than 5 years to figure out exactly what you can do in that. And then the next slide is about cell-free and full cell, and with $500 million market product potential and less. So as you can see, there is an empty spot there. We are still looking for someone in that empty spot, because that's where we want to invest. But we did identify somebody here in the cell-free that has the potential to go up there. So that's what we plan to invest. So my time is really up, and I want to say that it's illustrate our 4 process, which is predicting the future, not predicting like biomanufacturing is going to be large, for example, and then select. How do we select? And then build the companies, and then hope they are successful and become part of our ecosystem. So, okay, I'm going to skip that slide because my time is up. Thank you so much.